Eduardo González from University of Massachusetts in Boston. What crossing, what
Okay, so thank you very much for the organizers for the beautiful conference. And so what I am going to talk about today is joint work with Chris Woodward and Pablo Solis. And so the idea is to do some computations in quantum K-theory. And the formulas that I will present are not going to be as beautiful as in the previous talk, so they are much more explicit, and therefore they are going to be much more difficult to digest. But anyway, so the setup for today is just going to be, I'm going to take a projective smooth variety, and I'm going to take a polarization of that variety, and then I'm going to assume that G is a reductive acting on X, and I will denote by X mod G the quotient to stack, and then X mod G the GIT quotient. That means that I will consider the loci of semi-stable points with respect to the action, and then I will take the quotient with respect to G with that. So for today, I'm going to assume that this is smooth. In the case that this is not smooth and is Deligne-Mumford stack, there is also a theory for that, but the computations are a tiny bit much more complicated, and I will not address that in the talk. So typical examples, and these are the toy models that I want to test the theory first, are the Grassmannian and toric varieties. In particular, it's not, at least when I started this project, it wasn't clear if there were presentations, for instance, of the quantum K-theory for all toric varieties, and also a nice presentation for the quantum K-theory of the Grassmannian, so it was a nice point to start. But for now, now there are many people working on this particular problem, and so what I'm going to say is just one of the many ways of computing the quantum K-theory of those objects. In general, we're interested in much more general examples, equivalent varieties in the case when X is not necessarily smooth, but it has local complete intersections and so on. So perhaps in the future we will tackle those problems as well. So the topic that I want to talk about today as well is this concept that people use a lot, that is called abelianization. And so what I want to do is try to relate theories of the GIT quotient, the non-abelian quotient, with its abelianization, which is just given by considering the maximal torus inside G, and then looking at the semi-stable locus of the action of G inside the semi-stable locus of T, and then this diagram will relate these two quotients. And so in general, we want to, this one is a lot easier for most of the theories that I am trying to do, and so I want to say something about theories of the non-abelian quotient in terms of the abelian one. So for example, if you consider G equals just the general linear group acting on CK, I can take all the matrices that go from CK to Cn, and then the semi-stable locus with respect to the G action is, with the standard linearization, is just given by the rank K maps, the rank K matrices, and so the semi-stable locus with respect to the maximal torus, in this case I'm just going to take the diagonals, then it's going to be K tuples of non-zero vectors of size n, and so the quotients, on one side you have the Grassmannian, and the other one you have products of projective spaces. And so, as I was saying, the idea is to relate the difficult quotient in terms of the simple one. So quantum K-theory is part of Gromov-Witten theory. Ernesto told me that this talk was meant for students, that this was the easy one, so I'm going to repeat everything. I apologize. I just prepared the talk that way. So in Gromov-Witten theory, one is interested in the moduli stack of stable maps that go from a nodal curve with at most nodal singularities and some markings in there. They go from this curve into Y, and then modular automorphisms. The typical diagram that one draws, to get this Gromov-Witten theory is that there are some evaluations at the markings, and then there's a forgetful morphism that go into the Deligne-Mumford stack of curves, the compactification of that. And then the Gromov-Witten invariants typically are just defined, at least homologically, for instance, as integrals on the moduli space. And of pullbacks of certain classes, here you pull them back, then you integrate with respect to a virtual fundamental class, and then this is done by using a perfect obstruction theory in the moduli space. And so we're going to do the same thing, but just in quantum K-theory, so it's going to be something similar. I will define it later on. But then what I am going to do is trying to relate the theory of the quotient. So in this case, the y that I am thinking of is the quotient, the GIT quotient. But what I really want to do is to study the Gromov-Witten theory of the quotient through lifts of the theory above. So I am assuming that y can be presented as a quotient, and then I want to compute some sort of theory which is related to gauge sigma models to the original variety x that I had here. And so pretty much what I want to do is to study maps that go from a nodal curve into the quotient, the GIT quotient, but this sits in the quotient stack, and therefore I will start thinking of maps that go from a nodal curve into the quotient stack itself. And those things are called gauge maps. Well, I call them gauge maps. Some other people call them in different ways. And they are essentially pairs that consist of a principal G bundle over the curve that you have. So in this case, I am assuming that the curve is not nodal. So this is a smooth curve at the moment. And then together with an equivariant map that goes from the principal G bundle into X. And so this is equivalent to considering sections of the associated bundle. So the associated bundle is going to be P cross, so you change the fiber with the variety X that you have. You take the quotient by G, and then this is going to be another variety, another manifold that you, depending on the setting that you are. So, and then this map is equivalent to having a section like this. So in order to get a good moduli space, what we do is considering some sort of semi-stability conditions in these pairs. Okay, I will describe that in a second. And so this semi-stability condition will provide me with a nice moduli space that generalizes both essentially the moduli space of bundles and also the moduli space of maps that I am trying to study. So for the moduli space of bundles, there is in the general case, there is a semi-stability condition that was introduced by Ramanathan. And so I'm going to use that. I will try to define this in a second. And then for the general semi-stability condition that I am going to use is introducing Mumford's semi-stability for the target, as well as this Ramanathan semi-stability. And we call that Mondet semi-stability because Ignacy Mondet introduced this semi-stability condition in the case for symplectic manifolds. And so this is where we got the idea. And this depends on the linearization that I took for the beginning. So let's actually remember how this works. So I'm going to take the basic example of the projective space. I'm going to take, via representation of G, and I'm going to take the projectivization of that. So I'm going to take a character of G, and for the moment, you can assume that G is a torus, just to make it completely simple, okay? And then a polarization in this case can be taken just as O1, and then you shift it by the character. So this is the representation with character theta, okay? With this, it's just shifted. And so for any element in the Lie algebra, with the integral Lie algebra in the lattice, you can define a one-parameter subgroup. So with this, you define the minimal numbers of the pairings that you have. So if you break this representation into weight representation, so all of these are one-dimensional, and so you take the minimum of all the negative weights evaluated at lambda, this one-parameter subgroup, and this is the minimum of all the points where this is not zero. So x is a point in x, right? And so in homogeneous coordinates, it's just given by x1 to xn, whatever the dimension of this guy is. And then you look at the ones that are non-zero, and then you consider the minimum of that. So whenever you take the limit of that point, so you flow, right? So you flow with respect to this one-parameter subgroup. So the limit as z goes to 0 will completely be determined by this value that appears in here. So it's actually the point x lambda, such that its coordinates are either 0, and they are non-zero only in the case when this weight paired with lambda is exactly equal to the minimum of that. So this is essentially how it goes. And then this means that the one-parameter subgroup acts on the fiber of this shifted linearization, and then just by this value, okay, so the weight is this value that appears in here, and then the value of the character evaluated in the one-parameter subgroup. So this is what is called the Mumford weight in that particular case. And so you say that this point is semi-stable, I am assuming semi-stable is equal to stable, so if this is smaller or equal than 0 for all one-parameter subgroups. So x is going to be semi-stable if this is smaller or equal than 0 for all one-parameter subgroups. And this is equivalent to a complete combinatorial description So I can define the whole of of these weights, and then if theta happens to be inside the whole, then you say that the point is semi-stable. So it's a completely geometric characterization of semi-stability. And so now for the gauge maps, right, what I was saying that gauge maps are pairs, that is a principal bundle and a section, an equivalent section. But in this case, my target is a projectivization of a vector space, just an affine. So this is the same as projectivization of a vector bundle associated. So the P, well, this is unfortunately bad notation here. So this means projectivization. This is the bundle that I have, and so you can change them around. So there is a projectivization of the associated, this is a vector bundle in here, and so having a map that goes from a curve into the projectivization of a vector bundle is equivalent to having a map that goes from a line subbundle into this vector bundle that I'm present here. And so the sections that I am looking for are essentially just sums of sections of each one of these particular splits. So it splits completely, the V splits into all these one representations that you have. And so I'm going to call that the space of all sections. This tuples just W. Okay. So in general, you can at the moment you can see that these values over here may be may have common zeros, and those are going to define base points, and you can allow that, and that gives you a compactification in a nice way, in an algebraic way. So, and then these are combinatorial invariants that you associate to this pair. So the total degree of this thing is essentially the push forwards of C with respect to this pair. So think of this as a map. Remember, it was a map that goes from the curve into the quotient stack. And so it's going to be an equivalent class in homology. And then the projection that goes from into the cohomology, the equivalent homology of the point, you denoted by dp. So this is going to be the degree of the bundle that you have. And then, again, this is unfortunately a tiny bit of a problem. This L corresponds to the map U that you have. So this is a line, and so that's why I denoted LU in here. This L is the linearization that I chose in X. So there's unfortunately lots of L's that are going to appear here. So, but this one is the linearization. It has an equivalent first-general class that is going to be an H2G of X, which is this projective space. Remember, this guy is X. Okay, and then with that, the image of this guy, I'm going to denote it by theta, and this is the image that goes into the equivalent cohomology of the point, like that. And so du is going to be the degree of this bundle, because everything should be dualized. I have to put a negative sign in there. So the semi-stability condition for these pairs, in the particular case when X is equal to the projectivization of an affine, is just equivalent to having a shift. It's essentially the same as in the classical case of Mumford, but shifted by the degree of the bundle that I have in here dual. So it's pretty much not difficult to prove that this is the semi-stability condition for those pairs. And then you can define the moduli space. Over here, this bar is a tiny bit misleading. This is because I am allowing these base points, but in general, you can just ignore that, remove it, and then you can compactify them in different ways. So then this moduli space that I am trying to define is essentially just the semi-stable set of these sections, mod G. And so this is a construction for the moduli of gauge maps in this particular case. So as an example, just take G, which is just C star acting on a vector space of dimension k with weights, just the standard weights once. And then the degree in this case is just a split of the degree of the bundle plus the degree of the map that I had above. And so this moduli space of gauge maps is just going to be is just essentially a repeat of the affine that you have by the degree, and then this is d plus 1, and then you take 0, so you don't consider all the points at 0, and then you divide by c star, and that gives you just a projective space. So this is a lot easier to define than, for instance, maps that go from stable maps that go from a curve into a projective space, for instance. So this is a lot simpler. This type of spaces. And so that's the idea. You are replacing maps that go into the quotient, right? So this is what I am trying to say here. Into the quotient, the GIT quotient by this type of maps, but these are simpler in some sense. So this is the advantage. So the general case for semi-stability Let me just drink some water. The general case for semi-stability involves a lot of technical detail, and because this was meant for students, I am adding it here. So you usually take a parabolic reduction of the bundle, so Q is a parabolic of G, and then the Ramanujan construction goes as follows. So you take now lambda, which is a positive weight in the center of the Alevi decomposition of your parabolic. And then what you do is you form this bundle, which is P lambda. This is a bundle that is twisted by this one parameter subgroup. And the way you construct it is, well, if P is constructed by the cocycles, let's say psi ij, then the P lambda is constructed by these cocycles given by the one parameter subgroup twisting. So you take just the conjugate with respect to that one parameter subgroup. So that gives you a family of a C star of bundles over C. And then what you are going to do is you take the degeneration as lambda goes to 0. And then that gives you the graded object associated to P. And then, so you do the same with the sections. So you had a section that goes to the associated bundle when you have P cross X mod G. So in the case where you do this twisting by the lambda, the one parameter subgroup, so you also obtain a section and then you take the limit. So in this case, unfortunately for the section U, so this limit always exists because of my choice of positive co-weight. So that exists there, so this graded object for the principal bundle exists. But the graded of U is technically defined in the sense of González. So it will be a map that goes from a stable curve into the associated space in this case. So you have now this graded bundle, the graded object of the bundle cross X, so you change the fiber divided by G, and this is going to be a section of that. So I'm going to put that aside for the moment. And so what happens is that this stable curve that the person here will have a principal component where essentially the bundle will be on top of that principal component. So the picture that I like to draw is that if this was C, remember at the moment I am fixing that particular curve, C, and you can think that this is just P if you want. And then, so as it degenerates, it will have some rational tails, and the bundle lives on this part, so only on that. So it collapses on the other part. So the theory is not entirely complete. For the computations that I have in mind, it suffices. And so what I am going to do is to define this, the Mundet weight. I'm going to take the value. So this is mu bg is essentially the degree of the associated graded times the one-dimensional representation defined by the one parameter subgroup dual that I have. So you change that. So this becomes a line bundle, and then I divide by Q, which was the parabolic that I have. So I take the degree of that line bundle. And then this is this mu that appears here. And then this other one is just the Mumford weight associated to the bundle over the fixed point set of lambda. And so this is, the group C star defined by the one parameter subgroup is acting on that particular fiber, so that defines a weight. And then I will say that the pair is going to be semi-stable if and only if, this weight, this sum of the two contributions that I have is smaller than 0. So this is more or less how it goes. It's essentially just the semi-stability condition that you put on the bundle plus the semi-stability condition that you have on the target that you have. So this is more or less how it goes. And clearly, this parameter, this mu x, depends on the original linearization that you had. And so if you scale this linearization, the weight will scale, will scale as well. And so this is something that we want to exploit. One of the things that we do is to see how this semi-stability condition, the moduli spaces that are defined by this particular semi-stability condition, all of them are sitting inside the gauge maps. So what you are doing is essentially changing the moduli space that you have. And so we study that, and then we take the two adiabatic limits, one when k is equal to 0, and the other one when k is equal to infinity, and then try to relate the theories in that way. So as I was saying, there are two compactifications of these moduli spaces. The original one that I gave is essentially what we call the quote compactification, and there is going to be a compactification whenever you add markings as well to gauge maps, and this is going to be of very similar to González style. So the evaluation maps go and target into the quotient stack, so that's the only difference that you have, but other than that, it's essentially the same. And so there is a map that goes from the gauge maps with the compactification in González style that goes into the quad scheme compactification by just forgetting all the bubbles and collapsing them and sending them into base points. And so this is going to be a proper morphism. And one way of proving that these moduli spaces are going to be proper is by using this particular morphism. This is called Grünewald's morphism in general. Okay, so once we have this, then let's fix a particular degree. So this degree is, again, an equivariant degree in the second homology of X, or, Chow ring, whatever you want to use. So the theory in X mod G is these gauge maps that I defined. And the theory, I'm going to relate these maps to the theory on X mod G. Now, in the case as I define it, because I am picking a particular, so the bundle, I am assuming that the bundle only lies on a smooth component of this stable curve. So it's actually graphs. So they're not exactly maps, but they are graph maps. So I am picking a particular component that is isomorphic to my smooth curve that I had. And so the relation is that you don't have really the Gromov-Witten theory that goes into X mod G, but it is essentially the graph space that you have in there. So what we want to do is, to relate this guy and this guy, so those two moduli spaces, we have to introduce a cobordism between the two of them, and this is what we call scale maps. I'm going to define in a second what that is. And so this cobordism does not particularly relate these two on the nose, exactly, but it relates them up to corrections by affine gauge maps. So these affine gauge maps are essentially the geometric definition of what people call the mirror map in the Grünewald formalism of mirror symmetry. So this is exactly the type of geometric entities that are contributing to the quantum corrections of Grünewald formalism. So what are affine gauge maps? So they are going to be gauge maps that go from the projective space. So now I am assuming that my curve is just 0. And then you can do it in general if you want. And so it goes from the projective space into the quotient stack. But I am going to assume that the point at infinity gets mapped into the semi-stable locus of X. So this is the semi-stability condition that I am going to assume. And with that, you define those affine gauge maps as, just those particular gauge maps. And so the point at infinity is special. So this is what this means. It doesn't mean genus 0, genus 1 or something else. It means that I have n points that are going to map into the n points that, where is this? I think the endpoints that go into the quotient, this shouldn't be x to the n mod g, it's xg to the n. And then this one is the point at infinity, which is a special, and it goes into the semi-stable locus. So this is the GIT quotient. And so by pull-push construction, then you define what we call the quantum Kirwan map, depending on the theory that you have. But you can do the same thing in general. You can just define this type of maps for whenever you're working with Deligne-Montfort stacks or something of those lines. So this cobordism is given by a particular construction. So this was motivated entirely by a symplectic geometric construction that is called vortices. So gauge maps are essentially what people call gauge sigma models in general for a general group G. And so the construction in symplectic geometry is what people call symplectic vortices. So in symplectic vortices, this theorem was already established. This cobordism was established by many people, and Fabian Ziltener, for instance, were working on those type of things. And so what we do, what people did in symplectic geometry was to do the variation of semi-stability by increasing the area of the curve that you have. So the semi-stability was depending on the area on the curve. So in this case, we are doing something similar. So the area is what we call the scaling. And this scaling is just a section of the projectivization of the dualizing sheaf, the relative dualizing sheaf of C bar to C. So remember, because this is a map that goes from C hat, so this is a stable curve, into X mod G, into XG, then you just project on the principal bundle and to lie again on C. So there is a natural map that goes from C hat into C, and so this is the relative dualizing sheaf. And what this scaling really does is giving you a way of parameterizing which semi-stability condition you have to use whenever this scaling goes either from 0 to infinity. And so this is just a natural way of choosing semi-stabilities in between. Okay, so the theorem that I did with Pablo and Chris is that all these stacks are proper in the algebraic sense, and we gave a complete algebraic proof without using symplectic geometry, which is the proof that we had before. Anyway, so the cobordism, the actual relation that is important for any theory that you want to use is that as you push this, the linearization from 0 to infinity, is what you will obtain is that the moduli space of gauge maps will split, in particular to the moduli space of graphs that go into X mod G, and then with the correction terms that are the affine gauge maps that are appearing here. And so the formula that we have for this cobordism is that at infinity you essentially have a splitting of this guy in terms of corrections that appear in there. So it's an entirely geometric description. And so the whole point is that once you have this geometric description of gauge maps, right, and how they degenerate as you push everything to infinity, then you can apply this to any theory that you want. In particular, quantum K-theory. So we did this for cohomology in the past. And so quantum K-theory is just a generalization of quantum cohomology. So the only thing that you have to do is instead of integrating, you take Euler classes of sheaves. So I'm going to take K to be just the algebraic K-theory of Y. And then you integrate, well, you take this Euler characteristic or trace, but you have to twist by a virtual fundamental class on virtual fundamental sheaf. And then with that, for any two classes that you have, you can define the pairing, okay, by being the second derivatives of this potential. So you put all those Euler characteristics into a generating function. You call that the potential. This is just a formal ring of where all the coefficients are. Q is going to be, for the moment, just a formal variable, and these are the degrees. So you just attach everything in there. And by the way, you have to also sum over all possible degrees. And so with that, you just take the second derivatives that gives you the pairing. But this pairing is bulk deformed. Okay, so meaning that in quantum cohomology, the pairing is the same at every point in the Frobenius that you have, but in this case, the pairing is actually deformed at every point that you choose. So you have to be very careful about that. So it's an actual Frobenius structure that you get. The pairing is deformed as well. And so with that, once you have the pairing, then you can define the quantum K-theoretic product by just taking a test class and then take the triple derivatives of that potential in the direction of those particular elements that you have chosen. And so you can similarly do a G equivariant quantum K-theory just by introducing the action of G into Y, and then you do everything in that way. And then, of course, there is a very similar construction for the quantum K-theory of the GIT quotient. And in particular, what I am going to do is really taking the graph, what is called the graph potential, the K-theoretic graph potential, which only considers these stable maps into this particular space. So remember, you have a principal component that has been chosen here. And so, well, I'm not going to say what the virtual fundamental sheaf is. It's just very simply, if you have a perfect obstruction theory, so that's essentially gives you a cone in the E1 component of the perfect obstruction component. This is the dual of the E-1 of the perfect obstruction theory. And then you just take the left-derived tensor product inside E1 of the fundamental sheaf of Y with respect to, with the cone, which is, in K-theory, is just this class, is just the sum of the tors. So it's pretty easy to do. So there is a paper of Toen where he says that, really you don't need perfect obstruction theories to define the virtual fundamental class. You just need to use a derived structure. I am just putting it in there. I don't know why. I do not understand it yet. But, hopefully at some point I get to understand that statement. So cobordism, the cobordism that we had before, so remember this cobordism, the important one is this geometric animal, so I should probably point out. So this one is the one that is interests us. And so whenever you apply, say, quantum K-theory, really what it gives you is that in the limit, it gives you a commutative diagram that goes from the quantum K-theory, the quantum equivariant K-theory of X into the quantum the usual quantum K theory of X mod mod G, and then you have two potentials. So this potential that appears in here is the gauge Gromov-Witten K theoretic potential. This one is the graph potential of X mod mod G, K theoretic, and this one is, those are the corrections that you have to do, or some sort of a generalized mirror map. So this is what we call the quantum Kirwan map, just in analogy of what you have in a standard equivalent cohomology theories. And so by pull-push, as I was saying before, this map is defined. And so the theorem that I have with Chris proved it for cohomology. For K theory, it's not that difficult to define, is that as you push this to the limit, then this diagram commutes. So as you take the linearization to infinity. And moreover, the linearization of that map, meaning if you truncate the terms that have higher degrees, so if you just look at the degree 1 map, so that's like the linearization that you have, then this is a homomorphism in quantum K theory. So in particular, you can use this homomorphism to get relations in quantum K theory. So for instance, if you want to compute the relation for the projective space P2, then what you do is you present P2 as the GIT quotient of C3 by C star with the standard weights 1, 1, 1. And then let's say you want to find the relation for degree equals 1. And then the way you compute this is by studying the space of affine gauge maps with degree 1. And in this particular case, because my space is affine, it's very easy to compute. So what you have is just triples of polynomials of degree 1 that satisfy the summiability condition for affine maps. That is that at infinity, so that means at infinity, it has to be in the semi-stable locus of the action. That is, it cannot be 0, because 0 is the unstable locus. So in that case, the leading coefficients should be all of them non-zero. And so this is essentially what happens. This is the moduli space that is interesting for us. And a tiny bit of work, what it gives you is that that gives you the relation 1 minus x1 dual. The reason why x1 dual appears is because x itself, x in this case was C3, so x itself is just the sum of the representation. So it's x1, three times x1, where x1 is the C star representation of weight 1. And so the pullback at 0, so this is my marking that I have now. So this is the marking that I am using. So this is M11. This one marking tells me that I am using the linearization of the Kirwan map. And so if I take the pullback, this is also a K-theoretic class, but now over the moduli space of affine gauge maps that I am trying to compute. And so to compute this Euler class, you just take a section that appears in here. So the fundamental sheaf of the 0 set of this particular section. This section is just taking derivatives of the map that you have. So the Euler class of that is just given by the product of 1 minus x1 dual cubed. And this is just a pretty standard formula. And so what it means is that the Kirwan map, the linear part of the Kirwan map, will kill this 1 minus x1 dual cubed minus q. And so this has to be a relation in quantum K in the quantum K theory, or it's a expected relation that you have. So in general, for toric varieties, we expect that this is going to be true. So that the quantum K theory for any toric variety will have a Batyriev type representation. But I have to be a tiny bit careful here, because what happens is that in general, if the toric variety is non-Fano, then you will have some corrections. So what that means is that the quantum Kirwan map will have some sort of quantum corrections attached to it. So instead of x, over here is this isomorphism really means a formal isomorphism, where these x1s are not really the representations of weight 1 that appears in there, but it's actually some sort of the image on the quantum Kirwan map. So these have to be quantum corrected. Each one of the generators are quantum corrected, but this is the same presentation. And then they are formally isomorphic. I guess that's what I am trying to say. And so for the abelianization in quantum K theory, so this was the original problem that I have. So what I really want to do is to relate the quantum K theory of G and the quantum K theory for T. And so there is a restriction map. The quantum K theory associated to the torus, the big torus, it's a lot larger than this one. So what I do is you take the invariance with respect to the void, and then there is a diagram that goes like this. So you take the restriction. Now you take the quantum Q1 map that goes into the GIT quotient of the torus, right? So this abelian quotient. But then what I do is I have to twist it by some sort of contribution from an index bundle that comes from the root system of the torus that I chose. And so what the claim is that there is a commutative diagram that relates this. And in that way, the formal definition that we have is that, the formal result that we have is that you can compute this guy in terms of that. Well, not that guy in particular, but the whole composition of the potential and the quantum Q1 maps gives you a relation. So if you want the relations, then probably you can read them from here. I'm going to give an example probably at the end. And anyway, so we had some sort of work in this direction. We work in the small chamber, so when the polarization was K equals to 0, so we had this particular formula, which is abelianization in that case. But Dan Halper-Leisner pointed out a tiny mistake in our proof. And so it's now a true statement, but our proof was a tiny bit incomplete, and Dan was very kind to point out the mistake. And so in order to prove this formula in general, what we want to do is to start with the linearization in the small chamber, so that means when K is equal to 0, and then go all the stages, increasing the K all the way to infinity. But for that, we need to understand what happens in between. And probably, most likely, there is going to be some wall-crossing phenomena. And then this is essentially what we wanted to do. So the claim is that we can compute the quantum K theory, okay, in terms of this map that appears in here. So this is essentially that map. So the kernel of the map that goes from the quantum K theory of the abelian quotient into the quantum K theory of the non-abelian quotient is essentially, the kernel of this map is essentially given by a particular annihilator of a particular class that we know how to compute. And so this is more or less what the idea is in general. So there is going to be a big claim on that, but this is not yet proven. So in the last 15 minutes, I'm going to talk about wall crossing and a particular case that appeared and is related to rigidity, thus explaining the rigidity portion in my title. So wall crossing is trying to understand what happens to the two theories when you choose two different polarizations, right? So the diagram that I like to draw for explaining this is that you have two different GIT quotients. This GIT quotient in here should correspond to the L plus. This GIT quotient should correspond to the L minus. Two different choices of linearization, not necessarily equivalent. And so the quotients may change when you go from one side to the other. But over here, remember that what happens is that we are just choosing two different moduli spaces to do the computations. And so the relation should be a lot easier. What we do is to construct a complete geometric master moduli space that will parameterize, which will have the two moduli spaces of gauge maps as points at infinity. So this is going to be, the master space is some sort of parameterized by a sister action. The sister action will have fixed points given by this moduli space that corresponds to the polarization L minus, this one with the polarization L plus, and then some stuff in between that are fixed elements. And so what we do is, in order to do the computations that we want, we just apply virtual localization formulas in K theory, in this case because we want to apply it on the moduli spaces, and the moduli spaces have virtual structures, and then taking residues. Residues will mean that I get rid of all the Euler characteristics that appear in the virtual localization formulas in a nice way. So this virtual localization, I don't think I have time to explain that, so I will skip it. But then one of the things that happened is that when I was trying to do this, the formulas were just a complete mess. Because in cohomology, everything's somehow linear and beautiful, and then whenever you have something embedded in another space with weight 1, then the Euler classes are very easy to compute. It will be just like the equivariant parameter, and that's it, with a negative sign, and then over this side, it will be the equivariant parameter with a positive side. So the localization formulas are very easy. But in the case where you are working with K theory, that's not true. The Euler characteristic would be like 1 divided by 1 minus x, and the other one would be like 1 divided by 1 minus x minus 1. To minus 1. And so those things are not very well related. But there is a fix for this problem, and the fix is to, rather than working with the standard virtual fundamental sheaf, what you do is you work with the symmetrized virtual fundamental sheaf. So what this is if you do virtual tangent spaces given by deformations minus obstructions, right? So then you present them as let's say you have a group acting on them, in this particular case is C star, and then you present them as representations like this. These are characters of this action. And so the virtual fundamental sheaf you will be presented in this way, equivariantly. And so the symmetrized virtual fundamental sheaf would be just a symmetrization of this animal. You have to multiply by a square root of the anti-canonical, virtual anti-canonical class, which is in this case defined by that. And then in that case, there is a very nice restriction map that will get rid of the localization formulas that you are trying to use. So in this case, for instance, if you have something that goes, that corresponds to the action with weight 1, it will have, this would be the Euler characteristic to that, and so that would go to 1. That's cool. And then the other one would be the Euler characteristic with respect to the action that has weight -1, and that would be associated to that, and so that would be -1. And so with that in mind, then you can prove the theorem that I wanted to relate in this case. So that would give me the plus part, the minus part, and then these residues, these other contributions that come from the fixed point sets that are appearing here. So there is, I don't have time to talk about this, but how much time do I have? 15 minutes. Okay, so probably I do have time. All right, so then there is one case that people are very interested about, which is the crepant case. So whenever you have wall crossings, and the wall crossings induce some birational transformations, and some of the birational transformations that are very nice for some people are called crepant. And our representation of what crepant is really in this term of, in this way of GIT, is that whenever you do a wall crossing, if the fixed point sets of them associate to the action, so let me explain this. So let's say that you have a particular chamber here, so you're taking a quotient here and then taking a quotient there. So the fixed point sets that will contribute to the action are essentially fixed by a particular one parameter subgroup. And so that one parameter subgroup defines, there's this sister action in there. And so with respect to that sister action, those fixed point sets will be fixed by that sister action. And so if the normal bundles of those fixed point sets by that particular sister action decompose in a way that all the weights in the normal directions add up to 0, then that will give you what people call crepant transformations. And so in our case, when we want to use a wall crossing formula for relating potentials in one side of the wall and the other side of the wall, then we want to study very carefully what these contributions are on this side. In general, these are contributions that are in the gauge, at the gauge level, so gauge Gromov with an invariance. And so in this case, we did this particular analysis, right? So the analysis is that we can compute these Euler classes, which is in one side of the wall and the other one. And then what happens is that there is an action of the Picard group of the curve, which is just Z. And every single time, for each one of those actions, so the moduli space that contributes for those corrections in the wall crossing formula, they will have a class that is fixed, and then they would add up some other terms that are very symmetric. So in particular, for instance, the contributions that come from, let's say, an action, if the action in the normal directions is like of type 1, 1, -1, -1, the contributions on the wall for degree D, right, will be of the form 1 minus x, 1 minus x, which come from the negative terms. These negative terms would be like some sort of, on the top. They are not at the bottom because they are obstructions. And then this other Euler class would be of the form 1 minus x minus 1 times 1 minus x minus 1. And in general, this doesn't cancel. This is actually pretty nasty. This is not symmetrized. So this would be the contribution that you will have in that particular case. But if you symmetrize, then this will become automatically 1 on the nose. So this is a very rigid type of situation. And it took me a while to really realize that. But there is a whole factory of results that use rigidity. There is actually a paper by Witten that is called Rigidity of the elliptic genus, actually, what he uses the same idea that I'm going to use right now to prove that nothing happens, that every contribution on the wall is essentially trivial. So rigidity means that if you have a sheaf, and then you look at you know, anything associated to the sheaf, like for instance, in the homology, if the group is acting on the sheaf, and then if it's an equivalent sheaf, and then you look at the homologies, those are going to be representations. But if those representations are trivial, then you say that the object is rigid in that way. And so what happens in this case is that all of these contributions in the wall are going to be entirely independent of D because they are going to be symmetric. So the way of proving that is, I don't know if I said it in here. No, it's right here. So symmetric is, symmetric, rigid symmetric. So rigidity means that if you have a Laurent polynomial and it's bounded as z goes to plus or minus infinity, then Pz is constant. So in this particular case, all the contributions that I have on the wall, when you have a Crepin type of transformation, right, this wall crossing, all of them look of this form, okay? And so if rigid is if you have this equality of degrees, and then these guys are going to be the trivial representation with respect to the sister action. So they're independent on D. And so with that, then the sum of all those terms is essentially just given by a sum of Q to the D, which is a delta function. And so you can say that the two potentials in both sides of the wall, they are the same. So they differ by a delta function supported at something that, you know, Q equals 1 or something.
This is stable with derived categories in this case, and equivalence of derived equivalence. So
yeah, it should be. It should follow from there, yeah. But what I am saying is that, yeah, you're absolutely right. I didn't check that, but it's probably Dan has done it, maybe. I should take a look. But so in this case, we're just testing this type of theory. So it's actually true. There should be some sort of an equivalence, and it follows from if you take the K group, right? Yeah, that's right. I don't know. Are you familiar with this result? I mean, the funny thing is that this relates to rigidity, but there is as I was saying, there's lots of people that have worked on that, including, you know, the earliest paper that I found is Tia Hirzebruch, and then there is a work by Botten-Taubes. Well, Witten wrote a paper on that, and then Botten-Taubes wrote a beautiful paper on this, and then now Kunkov is proved some conjecture of Nekrasov using the same result. This is a trivial result. This rigidity means nothing, really. And so it's a pretty useful fact. Anyway, so in the last bit, what I wanted to mention is that we have tested, we haven't proven the abelianization yet, but we're working towards that. But in general, we tested this with known results, and so everything should work. So in particular, you know, let's consider, now this is going to be a tiny bit more in the style of Giventhal. So the K-theory, pick a basis for the K-theory where, you know, the unit is just the fundamental sheaf. And so for Giventhal, K-theory it can be completely determined by what is called the J function, quantum K-theory. And so you have this differential operator, and then the quantum differential equation says that you look at this connection that appears in here. This is quantum product, and then you have this operator, which is the derivative in the direction of these elements in the basis, and then you take this connection equals S equals to 0, so that gives you a covariant section, and then that's called the fundamental solution if it satisfies that particular equation. So the J function is just given by S minus 1, and then you evaluate on the fundamental sheaf, and then that's the J function. So the idea of Giventhal is that if you find any differential operator that will kill the J function, that gives you the relations in quantum K-theory. And so in the case that we have at hand, for the diagram that I draw, so remember that I had this quantum Kirwan map, I had my gauge maps, my gauge potential, and I had the graph potential in this side. So to relate the Giventhal formalism with what I just said, the only thing that you have to do is to, so if the curve is P1, then it also has a sister action that will fix 0 and infinity. So you localize the diagram with respect to that sister action, and then on the nose you will get, well, they are related, that this functioning here is the I function, so the gauge potential localized, let's say, at minus, would be minus is 0 in this case. So it would be the I function, and then if you localize this other potential would be the J function, and then the map that will relate the I and the J function is the localization of the quantum Kirwan map, and that gives you the Giventhal mirror map in there. And so there are some work people have discovered, what, you know, written very carefully what the J function is for P for a projective space, and also for a product of projective spaces. It's not difficult to write it from here. You just, you know, iterate, and that's fine. And also people knew what the J function of the Grassmannian should be. So I'm now going back to the original result that I wanted to show. And this is work by Taipale, Giventhal, Tonita, Iritani, and so many other people that probably escape me so at the moment. But then the differential operators, you can cook them directly. So as I was saying, operators that kill the J function gives you the relations in quantum K-theory. So we more or less try to find out what operators kill this guy, the product of projective spaces, and then we find and cook up what operators will kill the J function for the Grassmannian. And this is essentially what we did. So the operators, based on that, so we found the operator that is given by what is called a difference operator in quantum K-theory and some symmetrizers. And if you apply this one to the J function of the product of projective spaces, then you will obtain somehow the J function of the Grassmannians. But instead of that, what we did is trying to find a second operator that will give me the following relation. So I'm just going to say what the relations are because I don't have time for this. But if you define the Schur polynomials in variables ui, let's say, to be these particular polynomials, then what we can prove is that lambda over here is a partition. So you have a partition of the box, partition that fits in the box of k, n minus k. This is for the Grassmannian. So the relations that appearing here is if you have this Schur polynomial of, for the partition lambda plus n times mu. Mu is another partition of the same type. N means that you multiply the partition by n at every element that you have. And so if you evaluate on these polynomials, these are just the 1 minus xi v. So remember that over here you have k of those. Okay, so these are essentially the ones that come from the universal bundle on the Grassmannian. And then over here, what we get is that every single time that you multiply by n in this partition, you have to, it gives you a q out of the polynomial. The reason why that is because in the p function, so if you notice every single time that this guy increases by 1, then this should increase by n type of thing. So the relation gives you one extra one. Every n gives you one q, pretty much, that's what it is. And so with that construction of the relations, then we can prove that the actual presentation for the Grassmannian, so if these relations hold, that's equivalent to have a full presentation of the Grassmannian in terms of the Grothendieck Chern classes of the universal bundle. And then the relation that you have to impose in there is that the total Grothendieck polynomial, the K-theoretic total Chern class of the universal plus the universal quotient is equal to Q. And so that's equivalent to what our abelianization was saying. So pretty much what we want to do now is to relate these differential operators that kill the J function in terms of the differential operators that kill the I function. And then what you have to do is just to use the index bundles that appear in there coming from the root system. So that is this operator that presents that. But anyway, it's a tiny bit technical. I apologize for that, but so the formulas weren't as beautiful as the previous talk. I'll stop there, I guess.